Week 13, Thursday. This is the last lecture. Next week will be revision, and Tuesday will be revision. Thursday will be the exam. And today's topic is design and analysis of beams. Okay, so I'm going to work this out from an example. So the beam that we're going to look at, you can get this on Avenue to Learn. Okay, so this is the structure of our beam, right? This is the structure of our beam, and we are going to determine the maximum principal stresses acting on the beam. Okay, and also given the section used is W250 by 28.4. Okay, so this is the information of the cross section of the beam. Okay, so this is the information on the cross section of the beam. So the beam that we're going to use, okay, is this one, 28.4. Okay, so this is the information that's important to us, right? And then the cross section of the beam looks like this. This is the cross section of our beam. So if I were to draw our transformation, right? So this will be our X, and this is our Y. Or if we're going to follow this diagram over here, right? The cross section diagram, okay? Because it's good to follow the cross section of the diagram given, okay? So when that's the case, this will still be our Y. However, this will be our Z coming towards us. Z, okay. And then if you draw this, okay, then the X will rotate this way. Rotation about X. Okay, that's how we're using the right hand rule. Right. And before we go any further, right, the formula that we're going to use, or rather than the formula, we have to determine the position where Mx and stroke or Vmax, not N or, we have to determine where Mx and Vmax will occur. Right. So we know that there are two equations that we are going to use. Okay. So what we are going to determine, if we are looking at a 3D element now, right? And then this is our Z, if I were to draw our transformation, this is our Z, this is our Y, and this direction will be our X. Okay. So we have to find our stress Z, and then we also have to find, okay, we have to determine the shear ZY, and this one is the shear YZ. Okay, so we know that the stress Z, okay, so stress Z we know is equal to moment about X over IXX multiplied by Y. Okay, so IXX we know, okay. Y we also know. We don't know what is the value of MX. The next thing that we need to find out is the shear YZ is equal to Vy over IXX QX divided by T. Okay. So we have to determine the position where Vmax or Vn, okay, or comma Mx and Vmax will occur. So later on, we will plot the shear force and bending moment diagram. Okay, so to solve this, we have to plot, or we have to plot the shear force and bending moment diagram. Okay, right. Then we will from the plot we will find the different combination of V and M. Okay, so we have to find we have to analyze. Okay, so we have to, after we plot, we have to not find or analyze the different combination of V and M, okay, such that the principal stress, okay, stress 1 will be at its maximum. Okay, so this problem combines 3D Mohr circle to structure analysis. Okay, so first, I know some of you have forgot how about your shear force and bending moment diagram. I'm going to take like half an hour, okay, to revise with your dates. Okay. Okay, let's do the shear force and bending moment diagram first. Okay, let's do that first. Okay, so this is our structure. I'll go to the next page. Right, and then based on our transformation, this is our Z, and this is our Y. Okay, so the first thing we have to do is using static analysis to determine the reactions at point B and at point D. Okay, we're going to find the reactions. So we know from point A to point C, we have an evenly distributed load. Point B and point D is our reaction. Now, if you go back to our lecture long enough, week 1, okay, we had a more complex problem, yes or no? This is week 1 example, okay, or this is the example I showed you from the beginning of the week, okay, or beginning of the course, okay. So now we are going to do something very similar, okay, and then you will understand what we're trying to achieve in the introduction, okay, because this one was when you started the course, you find, wow, this is pretty complex, okay. Right, so now we are going to do using statistics to determine the reaction at point A, point B, and point D. So we start by doing that. So we will first thing we'll do our free body diagram, right? So we know that this is our beam, okay? And then we know that we have a by over here, and we have a dy, and then at a certain point, right, the equivalent load is 2.4, so 50 times 10 to the power 3 multiplied by 2.4 plus by 0.8. So 50 power 3 times by 50 power 3 times by 2.4 plus by 0.8 is equal to 160 times 10 to the power 3 Newton meter. I'll do it again, 2.4 plus 0.8 times by 50 power 3, 160. And the distance from here to here now will be equal to 2.4 plus by 0.8, and we divide by 2. Okay, so that distance is 2.4 plus 0.8 divided by 2, 1.6. Okay, so now we are going to apply static analysis. Okay, so some mention about moment in the x direction. Okay, positive is going anti-clockwise, is equal to 0. Okay, so we are going to do at point A. We're going to do at point A is equal to 0. So this is our point A. Point B is here. Somewhere down here is point C. And over here is point D, right? So when we take our moment about point A, we get 0.8. Okay, 0.8 multiplied by by, right? Then the evenly distributed load, the equivalent load is at 160, is going in a clockwise direction, so it's minus, right? 160, or a distance of 1.6 times by 160 times 10 to the power 3, and then we're going to plus sorry, I do apologize. I should not take moment about point A. I'm forming an equation that's absolutely useless. I do apologize. Okay, we're going to do point B. Why we should not do from point A? Because if I form the equation, I have two unknowns. I cannot solve for anything. Okay, so this whole thing is equal to 0. So we're going to take moment from point B, right? So 2.4 plus by 0.8 divided by 2 is 1.6. So that is 1.6. So the distance from here to here, right, is equal to 0.8. Okay. So taking moment from here is going to be clockwise, minus by 180, not 180, 160.